All right, so get ready, because today we are going deep into dark matter.
Ooh, dark matter.
Yeah, one of the biggest mysteries in the universe.
Absolutely. It's a fascinating topic.
And I know it might sound a little intimidating.
It can be, yeah.
But stick with us, because we're going to break it all down, and by the end of this deep dive, you'll be able to hold your own in any conversation about dark matter.
I think so, for sure.
So we're going to be exploring what dark matter is, the evidence that supports its existence.
Mm-hmm.
But also, and this is where it gets really interesting, we're also going to be diving into some of the alternative theories that challenge the very idea of dark matter.
Yeah, it's not a done deal.
Right, it's an ongoing debate.
Absolutely.
To get a well-rounded perspective, we've delved into a ton of sources for this one.
Yeah.
We're talking amazing YouTube channels like Star Talk, PBS Space Time, Veritasium, even a Joe Rogan clip.
Oh, wow.
Where Brian Cox explains the whole thing.
He's so good.
Yeah, he is.
He's a great explainer.
And here's the thing. This is where things get really wild.
Okay.
Some scientists are actually proposing that dark matter might not exist at all.
Yeah, that's right.
They're coming up with alternative theories like modified Newtonian dynamics, MOND. Yeah, exactly. Suggesting that maybe we just need to rethink gravity itself. So before we go down that rabbit hole, let's start with the basics.
All right.
What is dark matter?
So it's called dark matter for a reason.
Right.
It doesn't emit, absorb, or reflect light, so we can't see it directly.
Like it's invisible.
Invisible, yeah.
We're trying to understand something we can't see.
It's a challenge.
Okay, but if we can't see it, how do we even know it's there?
That's a great question. So one of the first clues came from this astronomer Fritz Zwicky.
Okay.
And he was observing galaxies in this cluster called the Coma Cluster back in the 1930s.
Okay.
And he noticed something weird. The galaxies were zipping around much faster than they should have been based on the visible matter he could see.
Right, because gravity.
Exactly. Gravity is what holds them together.
Yeah.
There wasn't enough visible matter to account for that speed.
So something else had to be there, something invisible.
Something unseen, something with gravity, something we now call dark matter.
So it's like, imagine a bicycle tire with water spinning really fast.
Okay.
You would expect the water to fling off, right?
Yeah, because of the centrifugal force.
Right, but in galaxies, the stars are staying put, even though they're moving super fast.
Yeah, something must be holding them in.
So that's dark matter.
That's the idea, yeah.
Okay, so Zwicky, he had this hunch about dark matter. What kind of evidence has emerged since then?
So one of the strongest pieces of evidence comes from the rotation of galaxies.
Okay.
This incredible astronomer, Vera Rubin, in the 60s and 70s, she studied how stars move in spiral galaxies.
Okay.
And what she found was pretty groundbreaking.
Okay.
She observed that the stars on the outer edges of these galaxies, they were moving way faster than they should if only the visible matter was contributing to the galaxy's gravity.
So it's not just like a few misbehaving galaxies, it's like a pattern.
Right, exactly. A widespread pattern across many galaxies.
That seems like pretty strong evidence.
It is, and this finding actually led to the concept of galaxy rotation curves.
Galaxy rotation curves.
So imagine you're plotting the speed of stars against their distance from the center of a galaxy. You'd expect to see the speed decrease as you move further out.
Right, that's like basic physics, right?
Right, but that's not what Rubin found. She found that the curves were flat.
Flat.
Flat, meaning the speed stays more or less constant.
Even far out from the center.
Even way out there, which implies that there's a halo of invisible matter, dark matter, extending beyond the visible part of the galaxy.
Wow, so if we could see this dark matter halo, it would be like a giant sphere enveloping each galaxy.
That's a great way to visualize it, yeah.
Wow.
Like an invisible scaffolding holding everything together.
Okay, I'm starting to get it.
Good, good.
Are there other ways, though, that we can see the effects of this invisible stuff? Because it's invisible.
So there are, and one really cool piece of evidence comes from something called gravitational lensing.
Gravitational lensing. Now that sounds cool.
It is cool. Imagine a massive object in space, like a galaxy cluster.
Okay.
It can actually bend the light that passes by it.
Bend light?
Yeah, it's like a cosmic magnifying glass.
Okay, so like those warped and stretched images of distant galaxies we see in those amazing space pictures.
Exactly, and by analyzing these distorted images, astronomers can figure out how much mass is causing that bending.
Okay.
And guess what? The mass we measure through lensing is way more than what we can account for with visible matter alone.
So it's like these massive objects are creating these invisible gravitational funhouse mirrors.
Yeah, that's a great way to put it. Bending light and revealing the presence of dark matter.
Okay, so we've got galaxy rotation curves, we've got gravitational lensing, all pointing to dark matter. But there's one more piece of evidence I want to talk about, the bullet cluster.
The bullet cluster is a great example.
It sounds kind of violent.
It's two galaxy clusters colliding
Wow.
at incredible speeds.
Okay.
And when these clusters smash into each other, the hot gas in each cluster, which is visible to us, it slows down and gets stuck in the middle.
So the visible matter gets bogged down in the collision.
Exactly. But here's the thing.
Okay.
When astronomers measured the mass distribution using gravitational lensing, they found that the majority of the mass wasn't where the hot gas was.
Where was it?
It was on either side of the collision, as if it had just sailed through without slowing down.
Wait, so the invisible stuff kept going while the visible stuff got stuck?
Exactly. And this is exactly what you'd expect if dark matter exists.
Because it doesn't interact with normal matter in the same way.
Exactly. It interacts very weakly. It just passes through.
Wow. Okay, so we've got galaxy rotation curves, gravitational lensing, the bullet cluster, all pointing to dark matter.
Pretty compelling, right?
It is, but we still haven't actually seen it.
That's true.
So the big question remains, what is this invisible stuff actually made of?
That is the million-dollar question, and the answer is we still don't know for sure, but there are some pretty wild possibilities.
Okay, I am ready to hear those wild possibilities, but I think we'll have to save that for part 2.
Sounds good. So we're back diving deeper into dark matter, trying to figure out what this invisible stuff is actually made of.
Yeah, that's the big mystery, right?
It is a big mystery, and unfortunately we can't just scoop up a handful of dark matter and study it.
No, that would be too easy.
Right, that'd be great.
So how do scientists even begin to narrow down the possibilities?
Well, they've been looking for subtle ways dark matter might be interacting with the universe.
Okay, so it's like searching for a ghost in a crowded room.
Yeah, kind of. You can't see the ghost, but you can look for its effects.
So what were some of the early ideas about what dark matter could be?
Well, some astronomers thought maybe it's just ordinary stuff that's hard to see, like clouds of cold gas.
Oh, okay.
Or faint stars, or even black holes lurking in the outskirts of galaxies.
So like the easy answers, check under the lamppost first.
Yeah, exactly.
But those turned out to be dead ends.
Yeah, we have ways to detect those things, and it turns out there just isn't enough of them to account for all the dark matter we need.
Okay, so what else is there?
So one of the leading candidates for a while has been something called WIMPs.
WIMPs.
It stands for Weakly Interacting Massive Particles.
Okay, that's a mouthful.
It is. It's a bit of a mouthful.
So these WIMPs, they're like these tiny particles.
Yeah, hypothetical particles.
That are really hard to detect because they don't interact much with normal matter.
Exactly. They're kind of like tiny cosmic ninjas zipping through the universe without leaving a trace.
I love that analogy.
And what's interesting is that WIMPs actually fit pretty well with what we know about the early universe.
Oh, really?
Yeah, theoretical calculations suggest that a lot of WIMPs would have been created in the Big Bang.
Okay.
And could have stuck around to become the dark matter we see today.
So the math kind of adds up.
The math adds up, but we still haven't actually found any WIMPs.
Oh, bummer.
I know, right?
So how do we even look for them?
Well, scientists have built these incredibly sensitive detectors, often located deep underground, to shield them from interference.
Okay.
The idea is to look for the tiny recoil that would happen if a WIMP bumped into an atomic nucleus.
Okay, so it's like a billiard ball collision, but on a microscopic scale.
Yeah, exactly.
Okay.
But these collisions are incredibly rare if they happen at all.
Oh, wow.
And they produce really faint signals, so it's a bit like trying to hear a whisper in a hurricane.
And so far, no WIMPs.
So far, no definitive detection. There have been some hints, but nothing that's been widely accepted by the scientific community.
And what about that Demolibra experiment?
Right, Demolibra.
They claim to have seen something, right?
They claim to have seen a signal consistent with dark matter, but they haven't released their data for other scientists to scrutinize.
Suspicious.
It has led to a lot of skepticism.
Rightly so.
Yeah, it's hard to evaluate their claims without access to their data.
Okay, so WIMPs are looking a little shaky. What else is on the table?
Well, there's another candidate called axions.
Axions?
Axions, yeah, and these are also hypothetical particles,
Okay.
but they're much lighter than WIMPs.
Okay.
And get this, they're named after a laundry detergent.
Wait, really?
Yeah, because they were initially proposed to clean up a problem in particle physics.
That's hilarious. I love it.
I know, it's funny, right?
Science can have a sense of humor.
Sometimes, yeah. So these axions, if they exist, they could interact with electromagnetic fields
Okay.
and produce detectable signals.
Okay.
So there are a number of experiments around the world using powerful magnets,
Okay.
trying to convert axions into photons, which we could then detect.
So it's like we're trying to lure these shy axions out of hiding.
That's a good way to think about it.
Okay.
But just like with WIMPs, these experiments require extreme sensitivity.
Wow, it sounds like the hunt for dark matter particles, whether it's WIMPs or axions, is really pushing the limits of our technology.
Oh, absolutely. It's a huge technological challenge.
But what if dark matter isn't a particle at all?
That's a really interesting question, and it leads us to a whole other category of theories.
Okay, I'm intrigued. What are we talking about here?
What if, instead of new particles, we need to modify our understanding of gravity?
Okay, so instead of adding new ingredients, we're tweaking the recipe.
Exactly, and these modified gravity theories, sometimes called ODE, suggest that gravity behaves differently at very large distances or in regions with very weak gravitational fields.
So maybe Einstein's theory of gravity, which works so well on the scales of planets and solar systems, needs a little adjustment when we're talking about galaxies.
That's the idea.
Okay.
And the interesting thing is that MO can actually explain some of the observations that led to the idea of dark matter.
Okay, like what?
Like the flat rotation curves of galaxies.
Oh, okay. So if MO explains those observations, why not just ditch the whole dark matter idea?
Well, it's not that simple. While Anna does a good job with some things, it struggles to account for other observations.
Like what?
Like the bullet cluster, for example.
Right, the colliding galaxy clusters.
Remember how the majority of the mass seemed to pass right through the collision?
Yeah.
That's hard to explain with just a tweak to gravity.
Okay, so it's like we have these two competing teams, Team Particle and Team Gravity,
Right.
each with their own strengths and weaknesses.
Exactly. And the debate is still ongoing. New evidence is coming in all the time.
Speaking of new evidence, you mentioned something about dark stars fueled by dark matter earlier.
Oh, yeah.
Now that sounds wild. I'm ready for my mind to be blown.
Okay, let's dive into that.
Okay, so we're back, and I'm ready to hear all about these dark stars. They sound pretty epic.
Yeah, they're pretty mind-blowing, and they might help us understand the very first stars in the universe.
The first stars, the ones that formed after the Big Bang.
Exactly. And, the prevailing theory is that those stars were powered by nuclear fusion, like our sun.
Right, right.
But some scientists have proposed a different idea. What if some of those early stars were actually powered by dark matter?
Stars fueled by dark matter. How does that even work?
Well, think about it. Dark matter makes up most of the matter in the universe. So in the early universe, when everything was much denser,
Okay.
dark matter would have been really concentrated too.
So picture a young star forming from a cloud of gas, but this cloud also has a bunch of dark matter mixed in.
Exactly. And if dark matter particles can interact with each other even a little bit, they would have been pulled into the forming star, accumulating at its core.
So you have this dense cloud of dark matter swirling around inside a young star.
Right. And as those dark matter particles get closer and closer together, they start to annihilate each other, releasing energy.
Annihilate, that sounds intense.
It is, but that energy released from dark matter annihilation could be powerful enough to heat up the star and keep it from collapsing.
So instead of nuclear fusion, it's dark matter annihilation that's making the star shine.
That's the idea, and because dark matter was so abundant in the early universe, these dark stars could have grown incredibly massive, millions of times the mass of our sun.
Wow, that's huge. We're talking about stars that would dwarf even the biggest supergiants.
Exactly, and they would have been incredibly bright too, shining brighter than entire galaxies.
So why haven't we seen any of these giant bright stars?
Well, because dark matter annihilates over time, these stars would eventually run out of fuel.
Okay.
And once the dark matter fuel is gone, the star's core would collapse, probably forming a black hole.
So these dark stars are like cosmic fireworks, shining bright for a while and then fading away, leaving behind a black hole.
That's a great analogy, and those black holes, those remnants of dark stars, might actually hold the key to understanding the existence of dark stars.
So you're talking about the supermassive black holes, the ones at the centers of galaxies.
Yeah, astronomers have always wondered how those supermassive black holes got so big so quickly.
Right, they're millions or even billions of times the mass of our sun.
Exactly, and it's hard to explain how they could have grown so large just by swallowing up matter.
So you're saying that maybe those supermassive black holes started as remnants of these ancient dark stars.
That's a really interesting possibility. If dark stars did exist in the early universe, they could have been the seeds for these supermassive black holes.
Okay, I'm starting to see how it all fits together, but is there any actual evidence for these dark stars?
This is where the James Webb Space Telescope comes in. Remember, it can see back into the early universe?
Oh yeah, those amazing images of the first galaxies?
Well, among those early galaxies, JWST has spotted 3 objects that are really intriguing.
What's so special about them?
Well, these objects are extremely bright and very distant, which means they must have existed in the very early universe. And here's the key.
Okay.
The light coming from these objects has features that are consistent with what we might expect from dark stars.
So we might actually have pictures of dark stars taken by JWST.
It's possible, but we need more data to be sure.
More data.
Yeah, the initial observations are promising, but astronomers are working to get more detailed measurements to confirm if these objects really are dark stars.
So the mystery continues, but it sounds like we might be on the verge of a major breakthrough.
It's a very exciting time, for sure.
Well, we've covered a lot of ground in this deep dive into dark matter. We've talked about the evidence for it.
Yeah.
Explored some pretty wild possibilities like WIMPs, axioms, MOND, and even dark stars.
It's been quite a journey.
It really has, and I think it's clear that figuring out dark matter is one of the biggest challenges in science today.
Absolutely. It's a challenge, but it's also incredibly exciting.
Because by trying to understand dark matter, we're not just learning about some invisible stuff. We're also learning about the fundamental laws of physics, the evolution of the universe.
Right. It's about understanding our place in the cosmos.
Exactly. It's a humbling thought, and it's really inspiring.
It is. It's amazing to think about all the things we still don't know.
And to all our listeners out there, remember, you don't have to be a scientist to appreciate the wonders of the universe.
That's right. Everyone can enjoy learning about these things.
So keep exploring, keep asking questions, and never lose that sense of wonder.
Absolutely. The universe is full of mysteries waiting to be uncovered.
Well, thanks for joining us on this deep dive into dark matter. Until next time, keep looking up.